I have a question. Is the time complexity of an algorithm same as that of the running or execution time of code? The answer is no. Wanna know why? Then hop on in and let's begin the journey with a scenario. John and David has been given a task to develop an algorithm which when given an input searches in the database and when found returns that input from the database. Next day both of them presented their algorithm for testing. John's algorithm took 90 milliseconds for 10 elements in the database and David's algorithm took 120 milliseconds. For 70 elements, John's algorithm took 110 milliseconds and David's algorithm retained the same. For 1000 elements, John's algorithm took 2 seconds and David's algorithm was at a constant 120 milliseconds. Now what's the conclusion? Whose algorithm was good? To answer this, you need to know about order and how to calculate order. Let's take a real-world example. You are given two algorithms which are used to search for digits from an array. One is linear search and the second is the binary search. Linear search is an algorithm which compares each digit of an array with the search digit. What do I mean by it? Suppose you have an array of 8 digits. The linear search algorithm would start comparing the search digit with the first digit of the array. If it was a match, it terminates the process. If not, it moves to the next element and so on. What is binary search? We have the same array of 8 digits. The binary search algorithm would start to compare with the first and the last digit of the array, and if it was not a match, it would navigate to the middle digit of the array. Here it checks whether it was a match. If not, it checks whether the search digit is less than or greater than the middle digit. If the search digit is less than the middle digit, the algorithm would navigate to the middle digit of the lesser digit, and the process continues until the search digit is found. Let's apply that principle to this example, where the binary search has to find the digit 10 in the array. First, it checks whether the first and the last digits are matched. If not, it tries to see if the middle digit is a match. Here, there are two middle elements, 7 and 8. We can consider any of them. Let's consider 7 and it was a match. Now, the algorithm would check whether the search digit, that is 10, greater than or less than 7, because it is the middle digit. Here 10 is greater than 7, so now 8 becomes the first element and the 12 becomes the last element. Now the algorithm would try to see if the first and the last digits are matched. If not, it finds the middle digit, that is 10, and checks whether it was a match, and yes, it was a match, and the process terminates. If it did not find the search digit, then the process continues. Coming back to the order, order specifies the number of operations done by an algorithm to solve the problem. Mathematically, order is called order, but in the world of computers, we call it as big O, which represents the time complexity. So, from now on, I will be calling it as big O. Let's calculate the big O of linear search. In the above scenario of 8 digits of array, it would require about 8 operations to find the search digit, since it compares every element of an array. So, in general, it would take n operations for an array of size n. Hence, linear search time complexity is big O of n, meaning as the size of the array increases, or in general as the input size increases, the time required to complete the operation increases proportionally to the input size. Now let's calculate the big O or time complexity of binary search algorithm. From the above scenario of 8 digits of array, it took about 4 steps to find the search digit. By the number of steps, we can identify a logarithmic relation between the number of steps and the input size of array. So its time complexity is log of 4, and in general it is log of n for n sized array. For those who has a fear or do not understand about log, just think that to find out the log of any number, just divide the number by 2 until it gets exhausted, and then add up the number of steps required for until the number gets exhausted. For example, let's find out the log of 8. Divide it by 2, it becomes 4. Repeat the step, it becomes 2, and then repeat it again, it becomes 1, which cannot be divided anymore. Now add up the steps required for you to exhaust that number. It was 3, and hence the log of 8 is 3. Let's plot a graph for our time complexities of linear and binary search algorithms. At the x-axis, you can see the size of the array, and at the y-axis, the time complexity or number of comparisons. The time complexity of linear search, which is big O of n, represents that as size of array increases, the time complexity increases. But in the binary search, as size increases, the time complexity increases slightly, which is great for practical applications. But of course, both algorithms have their own use cases. Here is a graph which represents the time complexity with respect to elements and operations. Big O of n factorial, big O of n square, and big O of 2 to the power of n are some terrible time complexity of algorithm where operations increases rapidly as the number of elements increases. Big O of n log n is better than the other three as its operation increases as the number of elements increases proportionally. Big O of n is better than the other four, and lastly big O of log n and big O of 1. These are the best time complexities of an algorithm as their operations remains constant, ideally as the number of elements increases. Coming back to our original question of John's and David's algorithm, to tell whose algorithm is better, we have to calculate their time complexity. Let us assume that John's equation for his algorithm in terms of input size is k1n square plus k2n plus 36, where k1, k2 is constant. While calculating time complexity, we can ignore the constant terms and consider only higher order value, which causes the equation to deviate. Here k1, k2 and 36 is terminated, and also n is terminated because n square is a higher order value compared to n. So the time complexity of John's algorithm is big O of n square. Now equation for David's algorithm is k1 k2 square plus k3 k2 plus k2. Applying the same principle, we ignore the constants k1, k2, k3 and 8, and we are left with 1. So the time complexity for David's algorithm is big O of 1 or big O of n to the power of 0. Because n to the power of 0 is 1, now you can judge by the time complexities whose algorithm is better. Comment it down. Before you hop out, get to know the answer for your question of why we do not measure in terms of time rather than operations. You have two computers. One has AMD E1 processor with an inbuilt graphic card and 1 GB of RAM, and the other has AMD Threadripper 5995WX processor with 6 NVIDIA 4090 graphic cards and 256 GB RAM. You give both computers an algorithm to solve. Which computer would solve the algorithm first? Obviously, it is the second computer. Due to this reason, we do not measure the time complexity in terms of time. And finally, David's algorithm was good. If you are still here, you have understood the most important building block of algorithm, time complexity. Congratulations, and signing out.